So very good morning to all of you. Myself Uma Sharma, Assistant Professor in EC Department, Ghaziabad, Ajay Kumar Garg Engineering College, Ghaziabad. Today in this lecture, we will discuss the biasing schemes of Mosfets. So in the previous lecture, we have seen the biasing methods for the bipolar junction transistor. So in this video, we will discuss the introduction of Mosfet, and then we will do the DC biasing of this Mosfet device. So there are a number of transistors which are available. One is known as bipolar junction transistor, then field effect transistor, and triac and thyristor is also comes in the category of transistor. Basically, the meaning of transistor is transfer of resistor. So here in case of BJT, we have already seen there is a change in the resistance from input to output side, because input is base emitter junction. If we talk about the amplification, base emitter junction is in forward bias and the collector base junction is the reverse bias. So input side resistance is less, and the output side junction the resistance is high. So there is a transfer of resistor from one end to another. So this is the actually definition of transistor. So here in this lecture we will focus on the FET part only. So FET is further classified into JFET and MOSFET. So again we will discuss only MOSFET. So further, the MOSFET is categorized into two categories. One is known as the depletion type MOSFET, and another is known as enhancement type MOSFET. In case of depletion type of MOSFET, there is a channel which is already exist between the source and the drain terminal. Basically, in the MOS device, there are four terminal. One is source, second one is gate, then drain, and fourth terminal which is known as body terminal. You can see the symbol of the AND channel enhancement type MOSFET. Whereas in case depletion type of MOSFET, you can see the symbol here. This line is solid. This represents that channel is already available to start the conduction. Whereas in case of enhancement type MOSFET, there is no channel between source and drain. There is a higher doping in the source region, but channel is not available. So first we have to form the channel for the conduction of charge carriers, then only we can start the operation of the MOSFET transistor. So here the symbol itself represents that there is no channel available between the source and drain. So symbolic representation is something like that. For N channel, this is the direction of current, and this terminal is your gate terminal, this is your drain terminal, and this terminal is your source terminal, and this is the fourth terminal which is body terminal. In case of NMOS transistor, basically the significance of this body terminal lies when we talk about the integrated circuit. But in the discrete circuit, we can short the base body terminal to the source like this. Whereas in case of P type of MOSFET, we can connect the body terminal to the drain node, which is most positive supply. So again I am repeating, in case of NMOS transistor, the body terminal is always connected to the least positive supply of the circuit. So if this is ground, then the body terminal is connected to ground. If it is minus VSS, then the body terminal is connected to minus VSS. Whereas for the PMOS transistor, the body terminal is always connected to the most positive supply of the circuit. So that is, in the circuit we generally connect the VDD as the most positive supply. So here the fourth terminal is always connected to VDD. So the direction of current is like this: drain to source in case of N channel MOSFET, and source to drain in case of P channel of MOSFET. The another difference between BJT and MOSFET is this: in case of BJT, there is a current conduction due to the two charge carrier. One is electron, second one is the holes. Whereas in case of MOSFET, the conduction of current is due to the one type of charge carrier at a time. Like if we talk about the N channel enhancement type MOSFET, so here the conduction of current is because of electron only. Whereas P channel MOSFET, the conduction of current is due to the holes. So here you can see the structure of the field effect transistor. So the source and drain terminal which is made up of N type, and here the substrate is P type. There is a silicon oxide layer which work as a dielectric between the body, means the substrate, and the gate node, and this is the gate terminal, and this solid black color shows the metal contacts. So for when we are talking about the enhancement type of MOSFET, so there is no channel between N and this source and the drain. But when we talk about the depletion type of MOSFET, the channel, the structure of device is like this. There is a channel which is already fabricated at the time of manufacturing. But for the enhancement type of MOSFET, we require to add some voltage at this terminal by which we can create a channel. The difference between depletion and enhancement type transistor is basically on the basis of fabrication process. In the depletion type of MOSFET, fabrication is complex because we have to design a proper channel at the time of fabrication. So it takes more area, it requires more effort. So enhancement type of transistors are preferred over the depletion type of transistors. So for the enhancement type transistor, the fabrication or the formation of channel is very easy. Like if we apply a gate voltage over there, which is positive gate voltage, then because is the P type of silicon, so the it sends the reverse force. So the holes which are available over here are gone like this, whereas if there are some minority charge carrier in P type silicon body that used to attract over here, so the voltage which is enough to collect enough amount of electrons over there is known as the threshold voltage. So if we apply a minimum voltage which is required to generate a inversion layer just below the gate is known as threshold voltage, and whenever this inversion layer is present, now we can start the conduction of current. This is the channel actually, which we have formed just by applying the gate voltage. So this is how a channel can be formed, and if we apply the drain voltage over there, then this drain voltage is used to attract the electrons from source end to the drain end, and the current flow of current is like this: drain terminal to source terminal, opposite of the direction of electrons. So for the MOSFET also, we need some biasing scheme by which we can stabilize the operating point. In the previous lecture, we have discussed the need of biasing. We have discussed what is the requirement of biasing and how we can bias a circuit through these biasing schemes. These biasing schemes we have already studied for the BJT, and the same are valid for the MOSFET also. The structure of MOSFET and BJT is totally different, but the operation, the function of both the transistors are almost same, because with the help of BJT you can implement two applications mainly. One is switch and second one is the amplifier. Similarly, with the help of MOSFET also you can implement switch and amplifier. So if we want to design an amplifier using MOSFET, because MOSFETs are preferred over BJT. BJT requires more area, BJT requires more power, and in case of MOSFET, the level of integration is high and it consumes less power as compared to BJT. So generally we prefer MOSFET over the BJT. So we should know how we can bias these MOS transistors. This MOS biasing is also known as MOS circuit at DC. MOS at DC. Because biasing is known as the DC analysis. Basically, biasing refers to the DC analysis of any circuit. So, for the biasing purpose, first thing is, in the circuit, if is there any capacitor, that we have to open circuit that these capacitors. Then, if there is any input signal AC source. So definitely the AC source should be isolated from the circuit, because we are actually calculating the DC points. So operating points means output current. These operating points means output current and output voltage. So this is the meaning of DC operating points. So with the help of fixed bias, self bias and voltage divider, we can bias the MOS circuit. So for the fixed bias, let's draw the circuit diagram. So if we are using a MOSFET which is N channel, again we are taking the example on N channel, and this is the representation of actually enhancement type MOSFET. I am not increasing the thickness of this second line, so this represent it is enhancement type of transistor. For the fixed biasing, you can add a fixed voltage at the gate, and this node can be connected to ground just by connecting a resistor RD over at the drain terminal. We can add this biasing voltage VDD, and here the coupling capacitor CC2 is used to provide V output, and similarly here CC1 is connected to couple the input signal with the MOSFET. So this is the circuit for fixed biasing. This VG we can also get from this VDD, like this. For example, if we remove this, one way is like we can connect directly voltage source, or with the help of this VDD by connecting a resistor RG, we can produce, or we can design a voltage source which is equals to VG. So in both the way we can implement the fixed biasing of the MOSFET. The only difference between the BJT and MOSFET is this: in case of BJT, we have seen that there is a small current IV at the base terminal which is not required, but we have seen the structure of the MOSFET. Here the channel is isolated with gate. That means there is a dielectric in between, that is SiO2 in between channel and the gate. So there is no current conduction from channel to gate. So gate current is always 0 in case of MOSFET. This is the simple rule, that Ig equals to 0. So here this gate current is always 0. This implies that this source current and drain currents are equal. If Ig equals to 0, that means Id is equals to Is. You can see this from the diagram. So here again I have to calculate Id. So if I apply the KVL in this loop, so we can write VDD minus Ig into Rg minus this voltage is known as VGS minus VGS equals to 0. So that means this term is 0, and this shows that your VDD is equals to VGS. This term shows that your VDD is equals to VGS. Now here you can calculate the you can apply the equation like this, the loop in the outer junction, that is VDD minus ID RD equals to 0. So here we need to calculate the value of ID. and from this equation we have seen that there is no current ID current component. So we should know the current equation ID for the MOSFET. We have to learn this equation. So if we want to design an amplifier, so for the amplification purpose, MOSFET should be in the saturation region. So again I am repeating, for the MOSFET there are again three type of operating region. One is known as saturation, second is active or linear, and third one is the cutoff. So for the switching application, this cutoff and the active region is used in case of MOSFET, whereas for amplification saturation region is used. So we should know the equation for saturation current as well as the linear current. In the cutoff region, the ID is 0. The cutoff region ID equals to 0. So in the saturation, this is the current equation, half mu n COX W by L VGS minus VT whole square. So here this mu n is the mobility of the electron, COX is the oxide capacitance, because MOSFET at the source at the channel region MOSFET form a capacitor. So we should know the value of equivalent oxide capacitance. W is the width of the channel and L is the length of the channel. So this is L is channel length and this W by L is known as aspect ratio, and this VGS minus VT is known as overdrive voltage, which is also represented by VOV. And also this represent that the value of VOV is directly proportional to the conductivity because ID is proportional to VOV square. So from this equation we can calculate the value of ID just by putting this VGS equals to VDD, because in our case we have add a fixed supply voltage VDD for this VGS. So that means in this current equation ID, mu n is constant, COX is constant, W by L is constant. Just by adding the additional supply voltage, we can get the value of ID. So if I compare the stability of BJT and MOSFET, then definitely the stability is also very much better in the MOSFET as compared to BJT, because in case of BJT there are different variation factors like beta, VBE variation, ICVO. There is no leakage current like which exists in the BJT, which is due to the minority carriers. So here with the help of ID you can calculate the value of this VDS. Sorry, this equation will be like this. VDD minus IDRD minus VDS equals to 0. So from here your VDS equals to VDD minus IDRD. So once you fix the value of ID, your VDS is also fixed. So this is how you can do the fixed biasing of the MOSFET. So the next biasing technique is the self bias or source biasing, because here we have added a resistor RS over there, and also we have added a RG resistor at the gate terminal, but here you can see that this current is 0. So the current in RG is 0. So overall, if I see the value of this voltage at this node, which is equals to the voltage at this node, and this is the voltage VGS. So if we apply the KVL in this loop, input loop, so here you can see that ID RD, this equation will be like this, VDD minus IDRD, just I have to write VDD minus IDRD minus IG into RG, which is 0, minus IG into RG, which is equals to 0. So minus VGS this voltage and minus Is into Rs, that is equals to 0. If Ig equals to 0, that I have already told you, Ig equals to 0, that represent that Id equals to Is. So in this equation, just putting the value of Is equals to Id, we can derive this expression. The value of VDD is IDRD plus VGS plus Rs into Id. So from here, you can calculate the value of VGS, and that is equals to VDD minus ID RD plus Rs. This is the value of VGS. In the previous case, we have calculated the value of VGS, which is coming equals to VDD, but in this case, the VGS is equals to VDD minus ID into RD plus Rs. That means this is reducing the value of gate to source voltage, and if there is any reduction, that means it is reducing the gain, but gain is reducing but stability is enhancing. So if you know the value of VGS, just write the equation for ID, and if transistor is operating in the saturation region, because we are designing amplifier, so ID equals to half of mu n COX W by L VGS minus VT whole square. So just by putting the value of VGS from this equation, we can get the value of ID, because this equation now is having the term of ID only, because this is the term which we can replace by Kn dash. So this ID will become Kn dash VGS minus VT whole square. So here this Kn dash is constant, Vt is constant. Just by putting of the value of VGS, we will get the equation in the term of ID, and from there we can calculate the value of ID. And to calculate the VDS, again we have to apply the KVL at the outer loop, and if we apply KVL in the outer loop, this is like this: VDD minus IDRD minus VDS minus ISRS equals to 0. So from here, VDS is equals to VDD minus ID. If IS is equals to ID, then that is equals to RD plus RS. So this is how you can calculate the value of VDS. If you know the value of ID, then easily you can calculate the VDS. And this is the most important biasing technique of Mosfet, which is known as voltage divider biasing. So here we have used voltage divider network, which is consisting of R1 and R2, and VDD is used to bias the circuit. So at the node X, we can determine the voltage. So at this node X, this Vx is represented by, just apply voltage divider rule. So this VDD multiplied by R2 divided by R1 plus R2 will be the value of this node, which is represented by Vx. Now if you know the value of Vx, you can apply the KBL over there, because the circuit is simplified, and these resistor R1 and R2 are parallel, but the current through the resistor R1 and R2 is 0. If I draw the equivalent circuit for this also, like the equivalent circuit will be like this. This is RD and this is VDD. Whenever we have calculated the value of Vx, then R1 and R2, this is R1 parallel R2, and here Rs is connected, which is grounded. So this is the equivalent circuit for this voltage divider network. But the current in these resistors, which is a parallel combination of R1 and R2, is 0. So if I apply KVL over there, then Vx is equals to this VGS plus Is into Rs. This should be Is, but we know that Is is equals to ID. So I can write this equation for Vx. Vx is equals to Vgs plus Id into Rs. For the saturation region, I have already told you the equation for drain current. So Id equals to half of mu and Cox W by L, Vgs minus Vth, which is the threshold voltage square. So from here, you can write the value of Vgs, and now put the value of Vgs in this expression. This is Vx actually, and you can calculate the value of Vgs, and then just by putting the value of Vgs in this expression, you can calculate the value of Id. So here you have to do one thing only, that you have to apply some biasing method. Like in that case, we have applied a voltage divider biasing, and by applying voltage divider biasing, we can calculate the value of Vgs in term of Id, and now putting the value of Vgs in the equation of Id, which we have already already know that in the saturation, this is the drain current equation. Then we can calculate the value of drain current, and this drain current is dependent on the parameter like mu n, Cox, length and width of the transistor, which is usually having constant value. The only thing in the Mosfet is the temperature, because this Vgs and Vth is nothing but a gate voltage, but this is the minimum required gate voltage, which is used to form the depletion inversion layer, sorry, not a depletion layer, which is used to form the inversion layer. So these Vgs and the Vth are the function of temperature. So here the problem is only temperature. There is no beta, there is no leakage current effect. So voltage divider biasing method is the better. If I compare it with all the biasing methods, it provides more stability, because here are more number of components in the circuit. So the tunability is high as compared to other circuits. So here in this lecture, we have studied about the Mosfet biasing schemes, where we have discussed the fixed biasing, we have discussed the self bias and the voltage divider biasing, and the overall the need of biasing technique we have discussed. So this is all from my side. Thank you so much.